Hi, everyone. Welcome back to Dave's Math Channel. I'm your host, David Terr, and today I have more of a philosophical than a mathematical discussion. I'm going to talk about whether mathematics is invented or discovered. And there's kind of two camps on this way of thinking. I guess some people think math is invented, some people think math is discovered. Maybe there's some people that think it's a little bit of both, but I'm more in the second camp. I think math is discovered, not invented. And there were if you want to go back to ancient times, this kind of question was asked by two very important philosophers in ancient Greece. On the left, we have Aristotle. He was in the camp. He believed he was a realist, not just about math, but about everything. He was kind of an objectivist. He believed in the existence of the material world. He thought everything ultimately was made of matter, and uh, I mean, a lot of scientists kind of think that way. I guess the basis of science is the belief that there is an independent existence of matter over mind. Plato was the opposite opinion. He thought um, you know, uh, mm, mind over matter. He thought well, he was a dualist. He thought there was a duality of the universe. There was the physical universe, which was made of matter, but then there was this ideal universe, his ideal forms. He thought that was kind of mind. There were perfect forms, and I kind of like Plato. At least as far as math goes. I mean, he thought there were ideal forms for everything, not just mathematical things. I don't agree with him about that. He thought there were ideal tables and ideal chairs, and I guess ideal whatever you could think of. I do think math, though. I do kind of agree with him about math. I think that there is an ideal math world out there. I mean, they're perfect spheres. You can define them mathematically, even though there's no perfect spheres in a real world. I mean, the Earth's kind of close, and but anyway, so I'm going to argue for mathematical Platonism, but first I have to give you some background. So these were the original two Greek philosophers that kind of addressed this question. But let's start by just starting with some very, very basics. I think most people I know are more in the math is invented camp, and I can kind of see why. I mean, when you first learn math, you kind of learn it in an Aristotelian way. I mean, when you first learn a count, what are you learning? Are you learning the number five? Are you learning the number five and the number six and the number three? I don't think so. You're learning how to count things. So, you start by first learning what a strawberry is, what different kinds of fruit are, and then, you count the strawberries. One, two, three, four, five. Five strawberries. I think it takes you a while before you realize that five strawberries can also represent five apples or five oranges, and it's really the number of the five that matters. But that's kind of a level of abstraction away from the real world. I think it's a little bit more natural when you're first learning about math to think of it in a more Aristotelian way. When you go to bed, you count sheep. And, the ancient people were like this too. I don't think, yeah, probably before ancient Greece, I'll bet that just about all the primitive people and ancient people who counted things, I don't think they really had concept of a number as an abstract thing. Maybe I'm wrong, but I think, the most ancient peoples, they were counting their flock, they were counting their sheep or their goats, or their fruits, and they were just saying that I have five sheep, I have eight goats, I'm not interested in the number eight other than the number of goats or sheep I have. Yeah, I think that came later. And what's interesting to me is that for some primitive societies, actually pairing is a more fundamental concept than counting. As a matter of fact, I know that there were some primitive African tribes who they didn't know how to count, but they knew how to pair things. And I don't know what they were called, but I learned this a long time ago. There was some African tribe that they had a bigger sense of a concept of parity, like odd and even. It would be harder for them to confuse 5 and 7 than it would for them to be confused 5 and 6. 5 and 6 were even though they were only apart by 1, you were more likely to, miscount as 7 instead of 5 and 6 instead of 5 because they had a strong concept of parity, which I think is kind of interesting. So if you think about it, pairing actually, you can actually, there's a lot of persuasive arguments that say that pairing pairing up objects is actually a more fundamental uh, form of math than counting things. This is kind of basic set theory. I mean, how do you know that there's the same number of elements in set A and set B? You don't have to count them. One way you can do is you can say, oh, there's 1, 2, 3 in set A, and there's 1, 2, 3 in set B. 3 equals 3. Well, there's an easier way. You don't have to know how to count. Just take the first object, pair it with another object in A. Take the second one, pair that with another object B. Keep pairing until everything's paired up and nothing's left over on either side. Voila. You can do that without even knowing how to count, which I think is kind of beautiful in a way. And I think there actually have been some primitive societies that have done this. They've known how to pair, but they haven't known how to count. I mean, we all learn how to count first, but I actually think pairing is more fundamental. Actually, and this goes beyond finite arithmetic. You can pair infinite sets. You can pair up elements of infinite sets. That's how you can measure sizes of infinity. You can't really do that with numbers. You have to first learn the whole theory of cardinal numbers, which is pretty abstract set theory that wasn't even invented till the late 19th century by Georg Cantor, who invented set theory. He came up with the concept of cardinal number. And there's a lot of seeming paradoxes involving infinite cardinal numbers. But I don't want to get too much into that. Anyway, I guess the point I'm trying to make with this is that, we don't have to start by counting. We can start by pairing. And then, I mean, I'm just going to go up through some of the math you learned when you were in grade school. Once you learn how to count, then you learn how to add. And I think you still added with objects. I mean, if you have 2 oranges in one set, 2 in another set, you just put them together, you get 4, and you count them, right? That's how people usually learn how to add. At least that's how kids learn how to add, right? They're not adding numbers. They're not adding abstract numbers. That comes later. They learn rules later for adding. First, they learn the abstract concept of a number. Once they're done counting fruits and objects, they start, thinking of numbers as their own kind of thing. And then they learn rules for addition. And, maybe it's when people start getting turned off on math because it's kind of abstract. You're dealing with these things called numbers that don't seem to have a real existence in our world. At least that's what I think a lot of kids seem to think. But I disagree. I think numbers are as real as fruits. And then first you learn how to add 1-digit numbers, and then you kind of, when you get better at it, you can learn how to do 2 digits and 3 digits. Of course, you have to learn about carrying and all that. So eventually you learn how to add anything you want. And then, of course, you learn all the other arithmetic operations. First, you learn addition, then you learn subtraction, multiplication, division. And if you go into more abstract math, you might even learn about modulus, which is really just a remainder. And this is all a computer needs to know to do any kind of arithmetic you want. And it's all really you need to know either. I think it's kind of unfortunate that modulus isn't taught along with division, because I think it's just as fundamental as division, but it seems a little more confusing to most people. It's just a remainder upon division. And I wish people would say modding by. It's not a verb. Mod is not a verb. I'd like to make it a verb. We mod 8 by 5 and get 3. I mean, the way most mathematicians prefer to say it, including my thesis advisor, you take the modulus after, you divide by. That's a lot more words. I just prefer say modding by. We say dividing by. So why not mod by, sounds a bit cool, like the mods from the 60s, I guess. But anyway, yeah, so those are the arithmetic operations. And what am I getting at here? I mean, here's what I'm getting at. So you can axiomatize everything we know about arithmetic. I think this is really, really beautiful, by the way. And this is why I'm a mathematical Platonist. I mean, who would have thought? Who would have thought? There's 7 axioms. These 7 axioms, and these look very abstract. They're written in the language of, logic, symbolic logic. Don't worry about that too much. If you don't understand these equations, don't worry about it. But they're really just mathematical equations for the axioms of arithmetic that this 19th century mathematician named Peano came up with. I think these are really beautiful. This is kind of the arithmetic equivalent of Euclid's axioms. So everything you have to know about arithmetic is defined by these 7 axioms. Once you have these 7 axioms, you can in principle, derive any result you want in arithmetic. Pretty beautiful in my opinion. So it's kind of the starting point for arithmetic. You didn't even have to know about counting sheep and counting fruits. You could have started with this. Of course, you'd be probably confused out of your mind when you started. But I guess if you were more like a computer than a person, this wouldn't confuse you. You'd just be programmed into your brain, and then you learn all the rules for arithmetic, and you know how to do any kind of arithmetic you want without ever even knowing what a sheep was or what an apple was. Pretty amazing, but I guess we're not computers. At least most of us aren't. Um, but maybe I've thought more like a computer most of my life than most other people. I'm on the spectrum. I have Asperger's syndrome, which I guess means that my brain's wired a little different from most neurotypicals. Maybe I thought about numbers as objects when I think I did. I think when I was like 5 years old, I probably thought of the reality of five more than the reality of apples. Um, I was happy with that. But anyway, maybe I think a little like a computer. I'm glad I don't anymore because I'm glad I'm human. I don't want to be Spock and I don't want to be computer. I don't want to be data. I want to fall in love. I want to enjoy some emotions along with my logical brain. I just have to continue to use logic to trump emotions, which is, I think, what everybody needs to do. But enough of that. Emotions are beautiful, but we have to control them. Otherwise, we might blow up the planet. That's another whole other issue. But anyway, let's get back to the subject. Yeah, so we learn the rules of arithmetic, pianos, axioms. These, by the way, only apply to natural numbers. Those are numbers, sometimes they're called whole numbers, but I think they include zero. And that's another thing I want to mention. I was always really, really amazed at the Greeks and the Romans. None of the ancient Westerners came up with zero. I mean, that amazed the hell out of me. They were pretty damn good mathematicians. I mean, the Greeks, as far as we know, came up with the whole concept of mathematical proof. And they were brilliant mathematicians, but it never occurred to them to think of a number called zero. And zero is fundamental. I mean, zero is part of piano's axioms. And I think without zero, we're screwed. I mean, computers wouldn't work without zero or negative numbers. I think the numbers become much more beautiful if we include zero and negative numbers. We have another video called Zero is Everything. And I'm glad that we know about zero and negative numbers, and not just that, but here's a Venn diagram showing all the sets of real numbers. So we start with natural numbers, sometimes called counting numbers, and here they do include zero. In the old days, they didn't even include zero. They called whole numbers starting with one. Or whole numbers started with zero. There were counting numbers starting with one. I guess it took a while for zero to really kind of get more and more accepted into kind of and a lot of mathematicians these days think it's more natural to start counting with zero rather than one. In computer science, we do this all the time. If we have an array, in computer programming, we always start it with an index of zero. It's much more natural than starting with an index of one. And it's kind of weird because centuries, people still debate whether centuries should end, the last digit of a century should be zero or one. Because, the first year, according to the Gregorian calendar, was the year one. There was no year zero. So, a lot of people thought that the 21st century began with 2001 rather than 2000. It's too bad there was no year zero, I guess. I mean, according to Back to the Future, Jesus was born December 25th, zero. So, maybe we have to adopt a new calendar where zero is a year. I don't know. But anyway, enough of that. So these are just different systems of numbers. And, the biggest set in this diagram is a set of real numbers. So first you have the natural numbers. That's the innermost set. Those are the first numbers we learn, including zero. I guess zero is kind of catching on. And then we learn about negative numbers, and they're kind of natural as today. At least if you live in a cold climate, you're probably used to temperatures below zero. And if you've done a lot of financial statements, you've probably been in debt at least once in your life, and you've probably had to record your debt as a negative number. So we're kind of used to those too. Rational numbers, those are just fractions. And I mean, this stuff took a while to catch on. Now a lot of this stuff is just commonplace. at least up to fractions. I think fractions are still commonplace for most people when you're cooking. You do 2 3/4 of a cup of water or something. That's not a big thing. I don't know how many people use square roots in their life. Probably most people don't. But beyond rational, we have real algebraic numbers. These are some types of irrational numbers. There's other types of irrational numbers in this outermost circle, pi, e, you know, so the collection of all rational and irrational numbers is the collection we call the real numbers. And I think most of us, are happy with real numbers. They make a lot of sense. We've seen a lot of them, and we're even kind of happy with irrational numbers, even though the Greeks were so unhappy when Hippasus proved that square root of 2 is irrational. The legend is that they had him drowned at sea because they just couldn't fathom the idea of an irrational number. It's very easy proof that square root of 2 is irrational. I do it in another video. But yeah, a lot of this stuff took a long time to catch on. And I think the latest kind of thing that happened in that regard, complex numbers. And I have another video on complex numbers. Those are just numbers with a real and imaginary component. And imaginary numbers are kind of weird. I mean, when I first learned them, I think my dad taught me about and imaginary numbers when I was about 10 years old. And when I first learned about them, I was thinking, what the heck? I mean, it didn't make sense there was a number you could call I that wasn't a real number. But eventually I got used to them. And I think the weird thing about imaginary numbers, I guess the reason they're called imaginary, is because they don't seem to occur in the real world. We don't have 3 + 4 oranges. We don't use eyes in our measurements, but they do occur in quantum mechanics. I mean, I think imaginary numbers are just as real numbers, actually. Even the physical world, we just don't observe them. The Schrodinger equation involves imaginary quantities. The wave function is an imaginary valued function. As a matter of fact, quantum mechanics wouldn't even work if it weren't. So there are imaginary numbers in the real world. We just don't observe them. But they're just as real numbers. And the set of complex, I have a whole nother video on complex numbers. Complex numbers are really, really beautiful. I mean, I think they're a lot more beautiful than real numbers. For one thing, the fundamental theorem of algebra says that the complex field is algebraically closed, meaning that every polynomial has all of its roots in the complex field, but not necessarily in the real field, even if all its coefficients are real. So in that sense, I think the complex numbers are more beautiful than the real numbers. And you can even go beyond the complex. There's quaternions and octonions and Sidonians, and quaternions are kind of nice. They get more and more abstract. You can actually do this infinitely many times. You can keep doubling the number of dimensions of these fields as an extension of the reals. Complex have degree 2 over the reals. Quaternions have degree 4. Octonians are what's known as Cayley numbers, I guess, have degree 8. I haven't worked with octonions. They seem like they'd be kind of a pain to work with because they're not even associated. You keep losing properties. That's the problem. You keep losing properties every time you double the dimension. So real numbers have the nice property that they're ordered. Complex numbers are not ordered, but they're algebraically complete, which is actually an advantage they have over the reals. Quaternions are not commutative with respect to multiplication. And then octonions aren't even associative. And, I think it must be a pain in the ass to work with a non-associative algebra. I've never done it. Maybe there's some beautiful things about octonions I don't know about yet. And then you go beyond that, Sidonians, the dimension 16 things. These things have 0 divisors. I mean, then you have numbers that you can multiply that aren't both 0, but aren't either 0, but their product is 0. And then, I mean, maybe there's some use for that. I don't know what. They get more and more abstract as you increase the number of dimensions. I'm happy with stopping with quaternions. The reason I like quaternions is because they're a really convenient way for working with 3-dimensional rotations. A lot better than Euler angles. As a matter of fact, they're more practical too. Like you don't get gimbal lock. There's a thing called gimbal lock, which happens if you're working with Euler angles. This was actually a problem on some of the Apollo missions to the moon. the gimbals, I guess the degrees of rotational freedom they were working with got locked, and then they couldn't really control the rotation anymore. They had to unlock it. And they wouldn't have had that problem if they were working with quaternions. So anyway, enough of that. And then, yeah, I just was talking about arithmetic. Now let's go to geometry. So just like we have Peano's axioms, let me go back again. Um, just like we have Peano's axioms for arithmetic, we have another set of axioms called Euclid's axioms. You guys are probably more familiar with these, are Euclid's postulates. These are the postulates, there's 5 of them. These are the 5 postulates that Euclidean geometry is based on. And for a long time, people struggled with a 5th one. That's the parallel postulate. This is written in a much simpler form than Euclid originally wrote it in. And this simpler form, is called the parallel postulate. The way Euclid wrote it down originally, it was like twice as long as this. And I think it was, who was it? It was what's his name? Playfair. Playfair in the 19th century, a British mathematician, came up with a parallel postulate and proved that it was equivalent to Euclid's original 5th postulate. So that's the one they usually teach these days. But the interesting thing about Euclid's postulates, they apply to plane geometry. For a long time, mathematicians were trying to prove the 5th postulate from the other 4. I mean, they thought, they could see it was a lot more complicated than the other 4, and they were wondering if you could prove that there was a unique parallel line, given for a given line and a point not on that line. And it turns out that you can have other geometries. They're called non-Euclidean geometries. I think Lobachevsky discovered the first one was called hyperbolic geometry, kind of the geometry of a hyperboloid, in which there's actually there's infinitely many parallel lines to a given line, and then later Riemann came up with spherical geometry, just the geometry of a sphere. You keep the first 4 postulates, and you discard the 5th one. You can come up with other geometries. Riemannian geometry, which is geometry of a sphere or a positive curvature, and then you have Lobachevsky geometry, which is geometry of a hyperboloid, which has negative curvature. So Euclid's postulates, actually, you can use them to define plane geometry. But before this was done, Euclid, these were around for over 2,000 years. Everybody just assumed they were true. They couldn't imagine any other kind of geometry. But I guess we started learning that we could play around with geometry a little bit and come up with other geometries, in which he changed some of the postulates. And I guess that's another point I'm trying to make here. I mean, you can think of this is his model theory, basically. In model theory, you start with a set of postulates, and then you see what kind of mathematical structure they create. So you can kind of define your mathematical structure you're studying by the postulates that it satisfies. So you can kind of play around with geometry, change the postulates a little bit, come up with different kinds of geometry. I don't think anybody's done this for arithmetic. We'd have some kind of weird arithmetics if we play around with Peano's axioms, I guess. I've never seen that done. Probably is possible. We get kind of weird stuff. But we have done it with set theory. At least I think we have. I'm not an expert on set theory, but there's these things called the Zermelo-Fraenkel axioms of set theory. And I'm not an expert on this at all. But I know set theory is a little weird. I mean, for one thing, I know that there was a thing called naive set theory in the 19th century before these axioms, and there was a thing called Russell's paradox. It was the paradox of the barber. There's a town that has a single barber, but the barber only shaves people in town who don't shave themselves. Then you get a paradox because who shaves the barber? If he shaves himself, then he doesn't, and vice versa, which is a logical paradox. And you can come up with even weirder paradoxes than that with naive set theory. The kind of the set of all sets that contain themselves, does that contain itself or not? And because he got all these weird paradoxes in naive set theory, Zermelo and Frankel, I guess, had to fix it. And actually, it turns out I think there's 2 different ways you can fix naive set theory. I mean, there's a thing called the what is it called? The continuum hypothesis. Is that what? Yeah, yeah. I think that's what it's called. Yeah, I mean, there's supposed to be there's these I don't know how much I want to get into this, but there's infinite cardinal numbers. The smallest infinite cardinal number is written as aleph null. That's kind of the size of the integers, the number of integers, or the number of whole numbers, which is the same thing because there's a bijection between them. But then there's also the continuum, which is the size of the real numbers, which is usually written by the letter C. But then the continuum hypothesis asserts that C is equal to the next infinite cardinal after aleph null, which people call aleph 1. So the continuum hypothesis asserts that aleph 1 is equal to C. And there's some versions of set theory in which that's true, and then there's others in which it's false. And I don't know which Zermelo-Fraenkel assumes. There's also the generalized continuum hypothesis that there's no cardinal number between aleph n and aleph n plus 1 for any n, any ordinal number n. I'm not an expert on set theory. One thing I'm not really happy about set theory, I know there's some set theorists that are very religious about what axioms they put into their set theory. And I don't know why they are. I mean, there's probably the equivalent of Euclidean and non-Euclidean geometries for set theory. There's probably, there are versions of set theory in which the continuum hypothesis is true, and there's others in which it's false. But for whatever reason, set theorists seem to be convinced that there's a real version of set theory that's true. Well, I don't believe that because mathematically that's not true. It's not any more true than the fact that plane geometry is just, non-Euclidean geometries are just as real as Euclidean geometries. I'd like to hear some of you guys' opinions about this. And there may even be other versions of arithmetic, like I've said. I'm getting into model theory now, but I guess that's a little bit off topic. I was trying to talk about where the math is invented or discovered. And like I said, I'm in the camp that I believe that it's discovered and not invented. Maybe I just contradicted myself because maybe we have to discover the true version of set theory or the true version of arithmetic. I really don't know. Uh, I might have just contradicted myself. But I have more personal reasons for being a mathematical Platonist. I'll give you three persuasive arguments. So now I'm done talking about model theory and all this abstract math. Now I'm going to get a little bit more down to earth again. And it's kind of weird. I show an alien when I say I'm getting down to earth. But just bear with me a little bit. The picture on the left, I actually did a video about this. These are the prime numbers up to 100. The numbers in yellow in this diagram are all the prime numbers up to 100. And the beautiful thing about prime numbers is that any extraterrestrial civilization that was discovering their own math, they would discover the same prime numbers as us. Prime numbers are universal. And that means that we could maybe use them to communicate with aliens because a prime is just a number whose only divisors are one in themselves, and that's universal. So, we could maybe use math as a language to communicate with aliens. That's why I think we discover the primes, and if there's an alien extraterrestrial civilization out there that also knows about primes, they would discover the same primes, and we could use them to communicate. We could send a signal, with primes as a beacon. I talked about that in another video. Not just primes, but we could use physics too. We could use physical constants like the speed of light or the wavelength of the HO line. Carl Sagan was a big proponent of all this stuff, and so it's kind of the universality that I think is a pretty persuasive argument that math has discovered. Because did we invent the primes? No. Because let's say we claim that we invented the primes. We Earthlings invented the primes. Well, then an alien would just you'd say they could have the same right to say we invented the primes. And then they could come to Earth and maybe we could have a big war with them. No, we invented it. No, we invented it. You stole them from us. That's kind of like how a lot of world history has been, but I don't think that's going to happen. I think what's going to happen is hopefully both us and the aliens will be enlightened enough to realize that we both discovered the same primes. Neither of us lays a claim on the primes. So primes are universal. And anyway, that's just one example. Another reason I believe that math is discovered rather invented Look at it, Maxwell's equation. I mean, this is one of the most amazing things I know about physics. I talk about this in another video. These are Maxwell's equations of electricity and magnetism. James Clerk Maxwell discovered these in 1864. Of course, he didn't write them down in this form. That came later by Heaviside, who came up with vectors. But it's pretty amazing to me. These four equations that are pretty simple equations if you understand the math. They explain everything there is to know about electricity and magnetism. I mean, imagine that. This kind of makes me believe in God. I mean, this is kind of like the argument from design. You know, the what do they call that? The cosmological argument. The argument that there seems to be an intelligent design behind the universe. I mean, this is one of the most persuasive arguments I've seen for intelligent design. Messed up, especially, when you look at humanity, when you look at the real world we have to live in, it seems like a mess. You don't have to look very far to kind of have that point of view. But if you study physics long enough and you learn about electricity and magnetism, and you learn that they have these universal laws, and it's not just the laws of electricity and magnetism. There's also laws like Einstein's law of gravitation, which is a beautiful single tensor equation, and we've got these beautiful equations that seem to kind of say how the universe works. To me, that's beautiful, and to me, that kind of points. I think Galileo had the same idea. He said God was a mathematician. It's kind of weird, a lot of people think that scientists don't like religion or they don't like spirituality. I don't think that's true. I think most of the greatest scientists in the world have actually been deeply religious or deeply spiritual. And I can kind of see why. I mean, it's funny because Galileo got convicted by the church. The church didn't like him, even though he was very religious in his own way. They convicted him because he proved that the Earth wasn't the center of the solar system. And they didn't like that. And even Darwin, who basically knocked down the story of creation from the Bible, came up with his theory of evolution by natural selection. Of course, the church didn't like him either, and there's still a lot of religious people out there that don't like the theory of evolution, even though to me it's as obvious that things fall. But people don't. A lot of people didn't like it because it contradicts the Bible. Same thing. So, but even Darwin was religious. I mean, I think Darwin was kind of ashamed of his discovery, actually. He was very well grounded in Christianity, before he went on the Beagle. And, he made his discoveries in the 1830s. He went to the Galapagos Island, I think, in 1834. But he waited 25 years till 1859 before he published his theory. And I think a big reason he did that was because he knew he was going to get into trouble. I mean, he knew he was going to get into trouble with the church. He was very, very cautious about publishing this theory, and but he was still religious. I don't know how he stayed religious after discovering the theory of evolution, but he managed to do so. And Einstein was religious in his own way. Einstein believed in God, but he was a Spinozian. He thought God was the universe. He was a pantheist. I'm kind of a pantheist too, by the way. I'm spiritual. I'm not religious in the traditional sense, but I do believe in God. And the main reason I believe in God is what I've learned through science. I mean, I just don't believe we live in this beautiful world that just, this beautiful universe that just got here on its own. I think God either created it or he is the universe. So, I used to be a agnostic. I was even an atheist at one time, but now I do believe in God, although not in the traditional sense. And but just getting back to mathematical Platonism, I mean, the fact that there's these beautiful laws of physics that we discovered these laws. We didn't invent these laws. We don't lay claim to Maxwell's equations. God gave us these equations to behold. You know, and any culture in the world would discover these same equations because they apply the whole universe. And even an extraterrestrial civilization would discover these equations. They probably write them differently, but they'd be the same equations. And the third reason I'm a mathematical Platonist, I mean, a lot of math, when it's first discovered or invented, depending on your point of view, it has no applications in mind. I mean, a lot of math, and I'm kind of a pure mathematician. Pure math Like these are what are called orthogonal polynomials. I'm not going to go into this detail, but these were discovered in the 19th century, I think. All these mathematicians, there's the Legendre polynomials, Chebyshev polynomials, Jacobi, Hermite, Laguerre. These were all just theory. This was just pure math when these guys came up with these things. They were just having fun, thinking about, well, let's play around with some interesting polynomials and see what kind of properties they have. Well, lo and behold, early 20th century, we had quantum mechanics. And it turns out that all of these polynomials have applications in physics. But, the guys who discovered these things didn't know about any of that. Hermite polynomials turn out to be involved in the wave functions of a one-dimensional harmonic oscillator. He had no idea that was the case. Legendre polynomials turn out to be the polynomials used in the quantum mechanical theory of 3D rotations or spherical symmetry. He didn't know that. So, there's been a lot of examples like this in math where there's been purely theoretical mathematical concepts that found applications later. And I find it hard to believe that that would be the case if these guys just invented these things, if they were just playing it, oh, let's invent a Jacobi polynomial, just for the fun of it. And then, if it was just invented, why should the universe have it? That's kind of what I think. So, if even a more dramatic example of this is RSA. This is kind of how the RSA crypto system works. And the RSA crypto system involves what used to be considered, I think even Gauss called it the queen of mathematics, which is number theory. For most of history, I'd say since Diophantus, he was like an ancient. He was, I think, first century A.D., maybe second century A.D. He came up with what are called Diophantine equations, which is basically just number theory, and there was no applications known for it. And this was true for, I think, almost 2,000 years, and that's why Gauss said number theory is the queen of mathematics, because he was convinced that there were no applications. It was purely theoretical interest, and it was kind of the domain of pure math. And Gauss was one of the greatest mathematicians who ever lived. And lo and behold, what happened? RSA, 1977, Ravesh, Shamir, and Adelman actually found a very, very useful application of number theory known as the RSA crypto system. They use these large primes. So, they take two large primes, multiply them together, and they come up with this crypto system that it's like a one-way crypto system. It relies on the fact that it's easy to multiply two large numbers, two large primes. It's also easy to check what a large number is prime, but it's much, much more difficult to factor the product of two large primes. And the algorithm involves some pretty abstract number theory. So, and this crypto system, whether you realize it or not, the RSA crypto system right now is what's keeping all of your internet information secure, all of your passwords, all of your bank account information, every account you might be using on the internet, like Amazon, whatever you're using, to buy your stuff or to protect all your account information. That's all being encrypted with RSA. So thank God for that, and thank God for mathematics, and that's just another example I can think of about how area math that was just considered pure math, no applications in mind at all. Um, you know, uh, Look how practical it became. Kind of like the orthogonal polynomials. So anyway, those are kind of my three reasons why I'm a mathematical Platonist. I also think in my heart, you know, I relate to Plato better than Aristotle. I used to be a hardcore realist. I'm not anymore. I think we need spirituality. I think Plato was a lot more spiritual than Aristotle. And it's kind of ironic in a way because Aristotle was a hardcore realist, and yet the church used his argument for almost 2,000 years to support their views. about the literal truth of the Bible. So they kind of twisted his realism as a way to defend their own religious views. So just think about that too. But anyway, that's my talk on mathematical. Is math invented or discovered? I hope you enjoyed it. Thank you for watching, and I'll see you next.